equal to 0. Let's try that. And then we'll look over here, when's the second derivative undefined. Let's do the undefined first. I think it's pretty easy to see when this denominator is 0.
I had a question.
Yes?
From whenever you pulled out the cube, the x squared minus 1.
It's not supposed to be cubed.
Yeah.
It's supposed to be.
What did I multiply top and bottom by just now? What was that 1?
3 times x squared minus 1 cubed.
It's just to the first power.
Yeah.
Yeah. What did I do? No, what I think I did is because the cube root was there, I must have looked at it and thought it was cubed when I rewrote it. Okay, so go back a line. Well, y'all say so. I told you I'm not all here today, and this is what I mean. Okay, look, go back one line. It's an easy fix. Remember where I said you had to introduce a 1 on the side? It should be 3 times x squared minus 1 to the first power over 3 times x squared minus 1. And then we had the 2 x squared minus 1. Is that right? No. Just 2 over the 3 times the cube root of x squared minus 1 squared. Okay, and I had circled this and I said this was our 1. I had put a cubed here and cubed here.
So
it's not.
To 6x squared minus 6 minus 8.
That'll be so much easier to solve. Okay. Now, I still had over here what? It was 8 x squared over what was supposed to be the common denominator, 9 x squared minus 1, then cube root of x squared minus 1 squared. I wrote cubed here twice. I put a cubed and a cube root when I initially wrote it down. It's like don't drink and drive, don't take medication and try and do calculus. Or algebra. This isn't even calculus, this is algebra, right?
So I got negative 2x squared minus 6.
Yeah, so let's just make sure. Is everyone clear on where I had fumbled that? Yes? Okay. For the rest of the class, if I do something obvious like that, just speak up. All right, so now when we put these together, this will be a 6 in front of these two. So I'll just distribute the 6 through. So we'll have 6x squared minus 6, but then this one over here is a minus 8x squared, then all over this common denominator, which is 3 times x squared minus 1 times cube root of x squared minus 1 squared, which is negative 2x squared minus 6. We'll pull a negative 2 out in a little bit. All right, that's a lot easier to work with, don't you think? Yes, that's going to be a little easier. So let's figure out where the second derivative is 0. So just set the top of that equal to 0. What? What's wrong? Y'all are looking at me again.
The bottom's 9, right? Yeah, it should be 9.
Ah, come on. Jeez, Robert. It's falling apart, man. I'm coming off the tracks up here. All right. I might just end class if I can't hold it together up here. I can handle like one mistake, but a 2 in a row, that's bad. Negative 2x squared minus 6 equals 0, right? And then set that to 0. Divide both sides by. So, what do you get? Hold on a second. Hold on a second. Yeah, there's going to be, it's not going to be a solution. It's not possible, right? Negative 2x squared equals 6. X squared equals negative 3. Can't have a negative root. No solution. But is it ever undefined?
Yes.
Second derivative, look down here. What's going to make this bottom get messed up? Same thing from last time, 1 and negative 1, right? We'll mess that up. So x is 1 and negative 1. All right, so number line. I only have 2 critical numbers, don't I? Okay. So critical numbers are negative 1 and positive 1. I'm plugging some test points into where?
Second derivative.
Second derivative, which is this beautiful thing right here that we worked so hard for. The top is always negative. You square a number, it's positive, but then times negative 2 is always negative. And then minus 6 still negative. So the top's always negative, agreed? Regardless of what I plug in. So all I really want to figure out is what's happening in the bottom. So try and do this without plugging it in and just doing it here, which I'm not trusting right now. So let's see if y'all get the same thing. Negative 2 squared, 4, take away 1, 3. So we're going to get positive number. Here, squared, oh, it's not going to matter here, right? This is always positive. So all that really matters is what happens right here. And I'm getting a positive there. So I'm getting negative over positive? Negative. So negative 2, you should get this. How about at 0? 0 there, it's negative 1 times 9, negative 9. So the bottom is negative. We said the top is always negative. So it's positive, so we get concave up. And then my guess is at 2, yeah, same thing, concave down. So we have 2 inflection points. Questions? All right. Let's put it all together, right? Graphy time. The points that are going to be interesting to us are the derivative points. Where they were 0, both the first and second. I think it was, what, 0, 1, negative 1? That was it, though, right? We have, let's see, all those points belong to my curve. Derivative, second derivative function. I believe it was on the first derivative, wasn't it down until we got to 0, then up from 0 on? Wasn't it like down like this and then up? And then it was what, positive, negative for concave? What was it to the left of negative 1? Was it down first?
Yes.
Down till we get there, then up until we get to 1, right? And then down. So I'm going to go down a frown, right side. Down a smile, left side. Up a smile, right side. Up a frown, left side. Do y'all see what's going to be kind of nice about plugging these points in? We already have, right? We already know what these points are. Just so happened that those turn out to be some pretty important points on our graph, right? So I've got this, 2 x-intercepts there. I have that y-intercept here. And remembering that it goes to infinity, right? Both sides go up. But watch, the way it goes up is different than the way it looks. So, look, I mean like over here. This one's supposed to look like the right side of a frown as I go up. So it's got to look like this as I go up to infinity. And then I'm going to go left side of a smile from here to here. That'll be a local minimum. And then from there to there, right side smile, left side frown up to infinity. There it is. Right? It's kind of tedious. Really, the thing I think that's most important with these graphing things is just that there's just so much algebra that can come into play with, function. When you look at its first and second derivatives, sometimes that algebra is very clean, sometimes it's nasty. Like this one was, I would say, in the moderate range of nastiness, wouldn't you? Like with the roots and stuff. But at the end, it wasn't too hard to figure out where it was zero and undefined. So what I, again, invite you to do are the problems that I had told you to do last time. I'm going to list out the ones I had planned to do. Some of these overlap with what I said last time. My original plan was to come in here and do 5, 8, 16, 17, 19, 25, 35, 43. I'm considering printing out the solutions to these and giving them to you so that you can go and do them on your own and then have something to check. Because I just don't have enough time to do this much work in this class. Do you all agree? I mean, that would just take forever. That's a lot of work right there. So what I think would be good at this point, I'm not going to break class yet. We'll break in just a little bit. But I think it'd be nice to see, like, something into the next section that gives you an idea of why we'd be interested in something like this. Why go through all this graphing stuff, right? I mean, it seems like that's a lot easier. Just use the computer.
Well, if it works properly.
If they did, right? That graph, that didn't look like ours, right? It's missing some stuff in there. And that's just, there's some problems with computers sometimes. They have trouble with evaluating certain things. So let's start with one of the more basic problems that you could imagine. Find dimensions, find dimensions of a rectangle with an area of 250 square feet that has the shortest perimeter. So let's understand the problem first, because this next section is word problems. I'm not formally introducing this section today. We'll do that next class. I just want to start thinking about this. So I need to come up with a rectangle, right, that gives me an area of 250 square feet. But I need to do it in a way so that the perimeter of this rectangle is the smallest it could ever possibly be. Any guesses as to what this rectangle is probably going to look like?
A square.
Probably a square, maybe? No. So let's just think, first of all, about some several options we could have. Let's just take a couple of different options. How about option A? Could I build a rectangle that looked like this? 1 and 250. And let's just say this is feet. Okay, so I'll put the little foot mark. Is that a rectangle that qualifies for that area? Does it have the area that's required? Yes? Okay, what is the perimeter of this one? The perimeter would be total distance around, which would be 502 feet. Right? 250 plus 250 plus 1, so 502. There are some students that believe, rightfully so, that if I draw another rectangle with the same area, the perimeter will also be the same. But it's not the case, as we're about to see. Option B. How about I do a 10-foot by 25-foot? Does that have the appropriate area? 10 times 25, right? That gives you 250. What's the perimeter of this one? 70 feet. Much less perimeter than this, right? Much less. And I could do an option C. I mean, right? Couldn't I? Yeah. So another option would be something like, I can make this up however I want. How about, what do you want?
550.
How do you mean? Oh, at 5, I thought you said 550, like 550 by...
No.
Yeah, okay, sorry, I misunderstood. 5 and 50, that would work. Agreed? 5 times 50, 250. So that has the appropriate area. What's the perimeter of this one? 110. So this one looked like, the option B looked better than option C, right? If we want to get the shortest area, shortest perimeter. But there might be one better than that. And that's where we get into the whole idea of the next section, which is called optimization. What we need to do is figure out what the dimensions need to be to give us the least perimeter without us guessing. Because how many different ways could we do this? There's an infinite number of ways we could build a rectangle with an area of 250, right? I could be some crazy ass that could say, all right, I want this side to be pi and this side to be 250 over pi. Does that have an area of 250? Sure. Perimeter? I don't know, whatever that is. But there is no restriction as to how I could make it. And it's impossible to check every option. So we need a better method, don't we? And that's where we're going to tie it all into the graph and maximums and minimums and all that. Make sure everyone understands the problem. Yes? Okay, so what I'm going to do, again, I'll formalize this more next class. What I'm going to do is first just draw a picture of just a generic situation, a generic scenario. So what about having a rectangle where I call this side x and this side y? So we want the minimum perimeter, don't we? Notice my choice of word here. I'm using minimum instead of shortest, right? In the word problem, I use shortest not to give away minimum. But now that we're thinking that this is going to somehow be tied to the graph of a function, I'm looking for a minimum value, right? Lowest value on the curve. I want the minimum perimeter, which means I need to somehow come up with the perimeter, right? This P as a function I can graph. If I can graph it, then I can find its lowest point, can't I? Yes? I should be able to find minimums. So since this is what we want to find the minimum of, I'm going to come up with an equation that represents the perimeter. So let's see. From this picture, what is the perimeter by definition?
P equals 2x plus y.
2x plus 2y. Agreed? That's what the perimeter is. The problem with this, as it sits, is that the p, as it sits, is not a function I can graph. Because to graph it, I need it to be a function of a single variable, right? Like just x's. So this by itself is not enough. Do y'all understand that? Like I would love for this instead to be rewritten as p of x where everything over here had x's in it, right? Everything on this side had just x's. Because then it, I graph it. Yes?
So can we differentiate?
Not yet. Well, you don't have anything to differentiate. Hold on, let me address this one first. If you differentiate, what would you differentiate with respect to? And why would you differentiate? You know what I'm saying? What we need is to first get the thing we're trying to optimize as a function of a single variable. In this case, either just x's, or you could just do y's, but as long as there's a single variable and not two. Now, if you take Cal 3, you actually don't need to do that. You can actually do this problem with the 2 variables, or with 3 variables, or 4. It's called Lagrange's method, but that's into Cal 3, and we can't do it here. Okay, we have to. This is what we've got. So, what we're going to use is a piece of information in the problem that we have to have in order to solve the problem, and that's this part right here. We know that this can't be just any rectangle, right? It can't just be any rectangle. It has to be a rectangle with an area of 250 square feet. This is what we call in these problems the constraint. I am not allowed, how do you spell that? Constraint. A? Does that look right? Constraint. Doesn't look right to me. AI? Who cares? All right. Okay, so we have a constraint. A constraint is kind of like a restriction, right? Like I can't just make x, a billion and make that 2. I mean, there is a restriction that the x times the y has to be 250, right? So I'm going to write that down. X times y must be 250. That is my constraint. And I'm going to erase this piece right here. So what I need is to be able to graph p as a function of x, right? Or as y. Except for the fact that the p right now has x's and y's in it. But my constraint is an equation that contains x's and y's also. So aren't I free to solve this equation for x or for y and then plug that into that equation? Yes? So take this constraint. Let's say we solve it for y. If we solve it for y, we get y is equal to 250 over x. And now come back and rewrite the perimeter function as 2x plus 2 times y, which is 250 over x. Now let's clean that up a little bit. The perimeter is now a function of completely one variable x. It is exactly 2x plus 500 over x. Right? And what do I want to know about that? Where is its
Where's the minimum?
minimum value? Right? I want the minimum of that. Now comes the important question. If I want to know when that's the smallest, am I on a closed interval or am I on an open interval? So think about x in the problem. Think about x. Do you have any control over x in this physical problem? Is there any sort of restriction on x?
Yes.
What would it be?
It's got more than 0.
It's got to be more than 0, right? Why can't it be 0? There's two ways to look at it. If x was 0 in this function, it would be undefined, wouldn't it? So domain-wise, x could never be 0. But also, for the rectangle to have an area of 250, if x is 0, the area is 0. So it's impossible to let x be 0 here. Agreed? X being negative, you're just crazy talk now, right? That's just crazy talk? I mean, in terms of this function right here, forget the rectangle. If I just threw this function up on the board, could x be negative? If I forget the rectangle, if I just said, hey, everyone, here's a function, can x be negative too? Yes. But within the framework of the geometry of the problem, can x be negative? It wouldn't make sense. So what we know right now is that x needs to be strictly greater than 0, right? So what I know for domain is that the x value has to be bigger than 0. Now, is there any restriction as to how big it can be?
It has to be less than 250. Right.
Does it?
No.
Could I make this side of the rectangle 500 and make this one 1/2? And that would still give you 250 area? Now this is a ridiculous rectangle. You would never want to build that. But there's no restriction as to me doing that, right? So I could not possibly check every possible scenario. So my interval, I can't restrict it either. I could have a rectangle that's 1 billion feet long as this side was small enough that when I multiplied them together, I got 250. So I'm never going to restrict it. So my domain is everything. So if I want to know when that's the smallest, don't I need to figure out when it's the smallest? How would you do that to try and figure out where that function is the lowest?
Take the derivative. And then
Take
see
the derivative, right?
what values are.
Yeah, just take the derivative and then, just like we were doing when we were graphing it, right? When we were doing our table and stuff, we were able to tell when it went down and came back up, right? Same exact principle. Except now it's not because we want to draw it, it's because it's solving a larger problem. Do you understand the difference? All we do the graphing for is to practice the method of actually attacking a function, seeing what it looks like. So what I'm going to do, I'm not going to go through the whole, let's do domain and symmetry and all that. I'm going to get down to the crux of the problem here. I want to look at the derivative, right? What is the derivative of this function? Well, it might help if I rewrite it because people don't like to take the derivative over there. They always want to use quotient rule. I don't know why people are so big about the quotient rule when you have x to the -1 like that. Right? That's what the original function is. It's much easier to take derivative of that. So the derivative here is 2, and then the -1 comes out. So -500 x to the -2. And then that's just 2 minus 500 over x squared, right? And what we like to do with that is now figure out where that was 0, right? And where it's undefined? Okay, so let me first try, where's that derivative 0? Well, I'm going to need a common denominator, aren't I? So get a common denominator between these two. It'll become 2x squared minus 500 over x squared. Right, that's what happens when I put those two together. And then really all I have to do to set the top of that equal to 0. 2x squared minus 500 equals 0. Move the 500 over. Divide by 2. Hey, there's 250. So x must be positive or negative root 250, right? Now I'm going to chunk the -1, right? Because my domain was only positive numbers. So x equals root 250. Is your conclusion that that's the minimum, that's where we're going to get the minimum? Is that your conclusion here? All you know is that that's a critical point, right? It's a critical number. Doesn't tell you that's a minimum. You have no idea if that's a minimum. Now, it's a pretty good feeling that that's probably the minimum, right?
Yeah.
But you have to show it, and it's very easy to show.
Plug it into the derivative.
Not quite. If we plug that into the derivative, we should get 0, right? Because that's how we got it. So how about we do this? Root 250, right? All I need to show you right now is what? To tell you that this is a minimum. Yep, that the function goes down then up, right? If I can show you the function goes down then up, would you be convinced? Yes? That's all I need to show you now. So I'm going to pick a test point. See how this is very much like the graphing? We're leaving some of the stuff out, though, that we don't need for the graph, because we're not trying to graph the function. So let's plug, I don't know, something over here. How about 1? 1, I love plugging 1 in. And then how about over here, anything we want, bigger than root 250? How about 250? 250 is bigger than root 250. And where am I plugging these in? Into the derivative. Remember, we're trying to figure out down then up, right? Down then up. Right? The only time you're going to be plugging into the original is when?
The closed interval method?
Closed interval method. Or when you're trying to figure out where specific points are on the graph. Okay, where's my derivative? It's long gone. Here it is. Here we go. That's my derivative. I got to plug in 1 into this. 2 minus 500 over 1 squared. 500 over 1 squared is 500. 2 minus 500, that's negative. Well, that's a good sign, right? Function's going down. Plug in 250. Hey, 250 squared is huge. 500 divided by that is going to be really small. And you can check it yourself. 2 minus that, it's going to be a positive number. I could have done it here too, into the derivative here, but it goes up. That's it. Hey, I didn't check where the derivative didn't exist. Well, I did, but I didn't bring it up. Why didn't I look at this, where it's undefined? It only happens at 0 and 0 not in the domain, right? This derivative could get screwed up at 0, but 0 wasn't even in the domain of the original function. So I did not include it on my picture. See, if I would have put 0 here, you would have tried to grab something from this side. That side doesn't matter to us, right? Those are negative values of x. So here's what I've got. I came up with a perimeter function. I was able to determine that there is one specific point at which that function has a local minimum. So to the left of root 250, the function goes down forever, right? Until I get to root 50, then it turns back up. And it goes up forever. There's no other low point on this graph, is there? This is the lowest one. So the minimum of p, I'm going to summarize now. P has a minimum at x equals square root of 250. Therefore, have I used the 3 dots? Yes, yes. Yes? Therefore? Did I use these yet or no? Okay, therefore, that's what this means. Therefore, the dimensions should be x is equal to root 250, and then we have to find the y dimension. Do you remember how we defined y, though? Go back to our constraint. Remember when you had the constraint and I said solve it for y? And we said y was 250 over x, wasn't it? So y must be 250 over x, but that's 250 over what we just said, root 250. And if you rationalize the denominator here, you get root 250. which means x has to be y, which means it's a square.
So,
Right?
5 roots of 10.
Pardon?
5 roots of 10.
Yeah, you could simplify that. Okay. Now, a different problem, similar to this one, but again, we'll do more of these as we move along here, would be instead of saying that the rectangle has to have an area of 250, what if we phrase the problem that you're going to have a rectangle, but this time you want the perimeter to be 250 feet. That's totally different, right? That's saying I want the total distance around it to be 250. Now find the dimensions which gives me the maximum area. So how do you think you should make a rectangle so that it has a fixed distance around it but gives you the most area? You think it's a square also?
Well, it's not a rectangle, though.
A rectangle is a square. A square is a rectangle, I should say. No, take that back. Every square is a rectangle, not every rectangle is a square. So, yeah, we'll address that. But it's a totally different problem. When we do this one, it'll be a closed interval method, because there is a restriction we can have on the x and y, because we only have a certain amount of perimeter to work with. So it'd be impossible to make one of these sides bigger than 250, right? Because you'd run out of perimeter. So that restricts our domain, and that problem will be a little different the way we attack it. So this is kind of where we're going. There's all sorts of cool things that we're going to look at. I think they're cool. They're just applications, but I think you should have a good rest of your day. Your homework is just to continue doing some graphing, all right?
We have an exam next week.
We are supposed to have an exam, I think, on the 23rd, which is next Monday, right? Yeah.
Will this be on there? The
Optimization, I probably included as maybe a bonus. Yeah. So what are we going to do then on Wednesday?